I have I have two announcements in terms of logistics. Number one, those of you who did the bachelor's here know how this works. We just started the exam registration period. That's important. It's not enough to register only for the class, but you have to register separately for the exam. And you can do so now until, I say December 5th, but that may be wrong. So do it quickly. Sometime early in December is when the cutoff is. Do you want to let us be part of your conversation? Okay. I'm sorry, I have to be a little bit strict here, but I'm teaching two classes back to back, and 3 hours yelling against students talking to each other just does not work. So, exam registration. We will have this year one exam period. We have set aside 2 weeks for our oral exams, which will start basically the Monday after the 19th. So we have basically February, I would have to pull up my calendar right now, but in February, 2 weeks, we will communicate that exactly once we get to the point where you register to the exam. So maybe I back up a little. Right now, you have to register for the exams on Ilias, on campus, to make sure that you can participate in the exam. Once the exam registration period has ended, we know how many people will take the exam. We will prepare the exam slots, and then we will send out an email to everyone saying we will have an exam period from 2 and ask for your input. Which of the 2 weeks is better for you? Are there any hard conflicts? And hard conflict means something academic. So you're doing an internship, you are heading back to your home university, you're heading out to study abroad, you have another exam. And you let us know basically your preferences and constraints, which will happen in sort of first half of December. And then shortly before Christmas, you should get your individual exam dates. At that point, it's important if you want to unregister for the exam. So if you signed up accidentally or you realize, okay, you don't really want to take this exam, you typically have 7 days prior to the exam to withdraw without consequences. Afterwards, you can only do so with a doctor's note. But that requires that you have an exam date. So you can because only then the system knows when is your exam and can basically calculate back 7 days to have this deadline for withdrawal. So in the system right now, the deadline for withdrawal, I think, is set to December 5th. As soon as you have an exam date, that will be updated. If you want to withdraw before that, let us know, and we'll give you a dummy exam date. So the system resets sort of the 7-day period, and you can withdraw. Question? Yes.
I'm just wondering if there's a class that only happens, say, for the winter semester, and say you decide you're not ready for it, would that test still be available after the summer semester, or only for the winter?
No, we offer exams twice a year, once after the winter term, once after the summer term. If sometimes people get sick, right, cannot take the exam. Sometimes they don't feel as prepared yet. Sometimes they fail in winter, and then they have to retake in summer. Yeah, good question. Any other questions about exam logistics, registration?
Are they in groups or?
It's individual exams. You get a 30-minute slot. And what is important is, I talked about this briefly in the first lecture, we'll get to this again a little bit later, is we have a project. So we have our exercises, 1, 2, 3, 4, 5, 6, 7 exercises, and then we have a project where the project is kind of in scope and volume, just another exercise, with the difference that we're not going to give you a template. right? The exercises are heavily guided. I hope you realize this. Here's your template, fill in the blank, do A, B in that order. The project is more build another robot. And you can work on the project in groups. You can work on it together. You have to hand in your own solution, both in terms of code and in terms of documentation, where the documentation is a 2 or 3 page document with the most important figures and just bullet points of what you did. Right? This is how I define things. This is where I simplified things, and so on. We try to keep that very lightweight. And that is going to be part of the examination. In the sense that we will talk about your project, and along the project we'll talk about how did you implement things, how did you do certain decisions, but also what's the theory behind this, right? Can you derive this equation? Let's look at this piece of code. Where does this come from? What is this term? What's the theory behind that term, and so on. So that project is quite important. And you see, right, this is our last lecture, and then you have another 2 weeks to finalize the project. But we actually are trying to give you even more time. This is why we present the projects already 2 weeks before the last lecture, so you can already get acquainted with it, even though at this point you haven't done your last exercise 7. Good. Questions?
The oral test, the type of questions would be like code-based or more theoretical-based?
Both.
Am I expected to understand every theory part being
Of course. Yeah, I mean, it's a theoretical class, but it has the strong implementation component. And I mean, the way you should think about this is, I mean, I'm doing this for 2 reasons. First of all, when you hand in your project, I already see that you can code. But I, as an examiner, want to make sure that this is your work. So we will ask what's happening here, what's happening there, why did you make that choice? Right? And if you wrote this code yourself, you will have no problems answering these questions. If you didn't, you're in deep trouble. So this is why we do this, right? But it's not only the implementation, of course, that we're interested in, but also the theory behind. But those two are tightly connected. So if I, point to a certain line in code that does some computation, I can ask you what's happening in the background. What is the equation? How does that equation work? What's the physical interpretation, and so on, right? It's all going to be a little bit more high level, right? This course is more about concepts than about doing math with pen and paper, because that part is basically replaced by writing code. Yeah.
So the theoretical questions are still going to be connected to the project, or are they also going to be like random?
They could be random, but in a sense, everything is connected enough that it never feels disjunct.
But you're not just going to pick a random chapter and tell me about constraints.
But I could ask you,
What about constraints
in the project, and then when we get to the lines that define the constraints, I can ask what other types are there, of course, right? So it's not enough to know that this is a rheonomic constraint in your project. Okay, any other questions about the exam? Still a while to go, right? And we will talk about this at length again. I just want to make you aware that now it's important to register for the exam. That was actually my only public service announcement. We are here. We will talk about recursive algorithms. We'll talk about topology linked lists. After class, there's homework, problem 26 and 27, which have to do with Jacobians. Right? There's some kinematic problems given, and you basically have to compute the Jacobians of here a point P, which correspond to a person sitting here on this little aeroplane, and then here we have a planar manipulator, I think in 2 versions. And again, the question is, what are the corresponding Jacobians? I'm mentioning those explicitly because I want to talk about, I think, problem 27 in class. So make sure you do this now, right? Some of these homeworks are maybe good preparation for the exam, but if you do this now, then you profit a bit more from our discussion in class. Any other questions about course logistics? Then let's dive right in. And in the last lecture, we basically finished talking about constraints. And I now want to start talking about robots and trying to start writing algorithms that let us allow us to do kinematic computations. So computing f of q, computing Jacobians, and so on. And I want to start with looking at these three pictures of mechanical systems or mechatronic systems that corresponds to different types, or I would say topologies, of connected rigid body systems. So this would be topology that we want to discuss. The first one, right, and let's just talk about different types of mechanisms. The first one is a standard industrial robot. And what it has is basically one end bolted to the ground. So what we have here is a fixed base. And then I get a very boring arrangement. I have a rotational joint. I have a link. Rotational joint, link, rotational joint, link, rotational joint, link, rotational joint, link. And at the end, a rotational joint. And then the last link, that would be the end effector. We would call something like this a kinematic chain, where each link is connected with exactly one joint to exactly one more link, and you basically go along links and joints in a chain from the base bolted to the ground to the end effector. Next, we have a so-called slider crank mechanism. Again, I start at a fixed base, right? So this is what you see here in sort of dark blue. That's a bearing that is somehow bolted to the ground. And in that bearing, you have your crank. This here would be the crank. So this is labeled here link number 2. And then it starts as if I'm putting together a kinematic chain, because then here I have a rotational joint, connects link 3 to here. I have another rotational joint, and then this would be here, this, I don't know, light brown last link here. So far, this would be a kinematic chain. But then in a slider crank mechanism, what happens is that this last link, the slider, is constrained to only move left and right. And that constraint is again bolted to the ground. And basically this housing here and the housing of this bearing, that's why they have the same color. They're both attached to ground. They cannot move relative to each other. I would call something like this a kinematic loop, because I start at some body, go through a sequence, in this case a chain of other bodies, and then end up at the same body, in this case ground, right? I start at ground, I end at ground, and I have a so-called kinematic loop. Loops can be annoying. Why? Overly constrained. The way I would interpret this answer is, how many degrees has this robot? You just count the joints, right? And this has 6 rotational joints, so I know that my end effector will have 6 degrees of freedom. This is typical for industrial robots, 6 positions, three positions, three orientations, can go anywhere in space. Some of them have a seven degree of freedom, so they have some redundancy built in. How many degrees of freedom does this guy have? 1, 2, 3, 4 joints, but 1 degree of freedom. If I want to represent this with an explicit constraint function, it's kind of easy to do, right? What would be my q's? Well, the 6 joint angles. And then I could compute the position orientation of the end effector, my x, as a function of these joint angles. If I try to do explicit constraints here, what would be my q? Right, now you have a choice because I have 1, 2, 3, and then the slider 4 joints. Which of these 4 should be the q that I use in my explicit constraint? So you would choose the slider, which I like as an answer. So first of all, you could choose anything, right? It's a design question. Some of these choices are better, some of them are not as good. Slider turns out to be actually the worst you can do. Why? It's not unique, right? So if this thing is moving in a circle, the slider goes back and forth. So if I do 2 pi here, I'm in the same position. So going sort of from crank angle to slider position is unique, but going from slider position to crank angle is not unique, right? You also have, sorry? Crank angle would be a much better choice, right? The other thing you have with the slider is you have once every cycle you have 2 kinematic singularities. These are called toggle points. If the crank is flat, this is at the maximum position here and cannot move independently, right? If the crank is in this direction, the system basically blocked. I cannot move the slider. The derivative in terms of velocities between here and here becomes 0. Is not invertible. This is very similar to this gimbal lock, right? And you would actually lose a degree of freedom here, right? If you look at sort of Jacobians of your constraints, you would see that this Jacobian becomes singular. Right? Here it's a little bit better, but we still have problems, right? So we see somehow loops can be tricky to model. What is the correct choice of q? What do we do to make sure that all the other joint angles follow exactly such that all constraints are fulfilled? However, you can do pretty cool stuff with loops. And I want to show you 2 videos. So this is what is called the Theo Jansen mechanism. Theo Jansen is a Dutch artist who builds walking machines that are all based on Q 4-bar linkages. Here you have a slider, a crank, pardon me. So this thing rotates, and then you have here your first 4-bar linkage, and then here you have your second 4-bar linkage. So 2 close kinematic chains. And what they ensure is that these legs basically step forward. Let me show you this again. They step forward and then move back in an almost perfectly straight line. Lifted up, moved forward, moving back in an almost perfect straight line. He spent literally years to come up with sort of this geometry, with this linkage mechanism, and it allowed him to build walking machines. And here's one of them. So this is made from welded steel plates, size about 4 meters high, and it now features a whole bunch of leg pairs made from this mechanism, and they're all connected with different phases to make sure that if one leg is on the ground, some other leg pair lifts up. And there he is pushing this mechanism, which must weigh a lot. But because the mechanism is sort of made that the legs move backwards in a perfectly straight line, the overall mass doesn't go up and down, right? And that makes this very, very easy to push, almost as if it is on wheels. Modeling the kinematics of this through an explicit constraint equation would be a nightmare. because you would take as an input your crank angle, and you would try to figure out what each of these other joints is doing, right? And they're all connected, right? There's a total of, I think, 9 joints in the system, but they're all some function of another, of the crank angle. So this is kind of difficult to do. Who's this guy? What's the name of the robot? You don't know. Oh, now I feel old. This is Marvin. Were you about to say this?
I didn't remember his name, but he's the depressed robot.
The depressed robot from Hitchhiker's Guide to the Galaxy, Marvin. And Marvin, again, is a little bit different. If I would start drawing a humanoid robot, I would normally start with some base segment. For humans and humanoid robots, that's often the pelvis or the torso. Here I choose the pelvis. And then I can go upwards. So this would be the torso of the robot. Attached to this, a very, very big head, which I here just draw as a little link. And then we have right arm, left arm, and we have 2 legs. And this would basically be the kinematic configuration of this robot. And first of all, we see it's not a kinematic chain, but we have here what I would call a tree. Right? In a kinematic chain, there's always one link connected to the next, connected to the next. Here, I have some links, like the torso, that are connected to one arm, another arm, the head, and the pelvis. And the pelvis also branches off, right? Pelvis connects to 2 legs and the main body. So that's one difference. The second difference is that this robot is not connected to ground. You could argue that it's standing on the ground, but I showed it here in a short moment of joy where we're so excited to jump in the air, which rarely happens with Marvin. But now it's not connected to anything. Down here, right, this would be a unilateral constraint. And that means I cannot use that constraint as a connection to ground, right? It could be that the left foot is on the ground, it could be that the right foot is on the ground, both, but it can also happen that none of the feet are on the ground in such a humanoid or legged robot. So I have to somehow make sure that I have another connection to ground. And this is where I will introduce what we will call a virtual 6 or virtual 3 degree of freedom joint in planar systems. So in 3-dimensional systems, we would have a joint that has 6 degrees of freedom and that does not have any motors or doesn't create forces and so on. It's just there to basically monitor where the pelvis is moving relative to some fixed reference. This would be a virtual 6 degree of freedom joint. So not a true constraint, but something that allows me to track the position of the pelvis in terms of 6 variables, 6 cues, that describe sort of the relative displacement and relative orientation of the pelvis to the ground to base. We would also call this a floating base description. And since we don't want a floating base, right, we would like to have, for the kinematics, some fixed base, we introduce this virtual joint. Right? It doesn't constrain motion because it has 6 degrees of freedom, and importantly, you're not allowed to assign any torques there because there's no motors. I can assign a torque to the knee. If I then do a controller, I can assign torque to the hip and so on. But I cannot assign a torque to this virtual 6 degree of freedom joint because that would be literally someone grabbing the robot and lifting it up and moving it around. For now, we want to exclude loops. We'll save them for later, just to simplify things. And we basically, whenever we get such a floating base situation, right? You have this in humanoid robots, you have this if you talk about drones, everything that is not somewhere rigidly bolted to ground is basically floating base. Whenever we have that, we introduce such a virtual 6 degree, or in the planar case, 3 degree of freedom joint. And this allows us to treat every system as what we would call a kinematic tree, including these kinematic chains, which are just then a special case of a kinematic tree. So this is what we will do in the next couple of lectures. We treat all systems as kinematic trees. And that simplifies things a lot, because when we do this, we can simply go ahead and assign each joint or each motion primitive a Q. Right? So we can assign a Q to each motion primitive to each degree of freedom. And because there's no kinematic loops, the number of degrees of freedom will be equal to the number of Qs. We can then go ahead and use explicit constraints and compute X, where X could be the position and orientation of every body in our kinematic tree, as a simple function of these Qs, and if we have a rheonomic system, time t. And similarly, we can compute our velocities via the associated constraint Jacobian JF times Q dot plus, right, if we have a rheonomic system, partial FC, partial time. To make that work, we always need a connection to ground, right, to something that does not move, something that is at a defined position and orientation of 0. And if we have a floating base, then we just go ahead and use these virtual 3 or 6 degree of freedom joints. And what we don't do are loops and inequality constraints. So what we see here as well, right? If the foot is on the ground, I would have a kinematic loop created through this ground virtual 6 degree of freedom joint, the joints in the leg, back to ground. If I have 2 feet on the ground, I actually have 2 loops. So it makes sense to treat these inequality constraints together with loops. And for now, basically fix them by having a a virtual connection somewhere else, and then say, okay, these these inequality constraints will later go ahead and create loops, and we deal with these later. And what our goal is now to represent this in a computer, right? That is basically the forward kinematic problem. So develop a formalism to represent arbitrary trees. And then compute these explicit functions, right? So compute fc and jf in some efficient way, and this is called the forward kinematic problem. And in a sense, right, this is not a difficult problem. If I give you a drawing of a robot and I say these are the joint angles with, this is how they're defined, Q1, Q2, Q3, these are the dimensions, you could probably sit down and figure it out, right? There's some sine, cosine terms, you have to do a little bit of trigonometry, but especially in the planar system, it shouldn't be difficult to figure out the position and orientation of each segments once you know the Qs. Right? So it's not a hard problem, but it's something that can be very tricky to do well, especially if your system gets very complicated and your system is three-dimensional, has different types of joins, and so on and so forth. So we want to talk about now talk about algorithms, developing algorithms to solve that forward kinematic problems for arbitrary trees, with arbitrary topologies, with, in a sense, almost arbitrary joins that you then can put together to generate whatever robot, whatever system you want to look at. If I think about abstraction, I have somewhere a physical system which can be simplified if you think about a dynamical system, and we've seen this, right, that in terms of dynamics, if I have a body, there's three things that I care about. Its mass, its inertia, and the location of the center of mass. If I know these three things, I know what that body is going to do, no matter what color it has, how it's shaped, how long it is, and so on and so forth. Right? So in a sense, this would be your first level of abstraction, where I say I represent my robot, I represent a human that I would like to simulate simply through bodies which have mass and inertia. If I only care about kinematics, I don't need to know that as well, right? All I need to know then are dimensions and locations of joints and joint types, right? I need to know what is connected to what at which location with which joint. And I can even go one step simpler when I just think about what I would call the topology, is this idea of what is connected to what. If I think about the system here as saying this is ground, I have link 1, link 2, to be consistent with my notes, 2, 3, 4, 5 would be the legs, 6 would be the torso, 7 would be the head, 8, 9, 10, 11 are the upper and lower arms, respectively. I can set up a graph that just tells me what is connected to what. So I have ground, which is connected to link 1. Link 1 being connected to link 2 and link 3, being the upper legs, which in turn are connected to the lower legs, link 4 and link 5. This link 1, the pelvis, is also connected to the torso. Link 6 or body 6, that is connected to the head and to the upper arms, which are bodies 8 and 9, and those in turn are connected to the lower arms, bodies 10 and 11. And what we see here is a graph, right? A mathematical graph with nodes and edges. So we have here the representation as a graph, and there is a direction built into this. And the direction, I will highlight this with arrows, is basically going outwards from ground. Ground is special. It's going to be the root of our tree because ground, we know, is not moving. It's stationary. And the motion of each body only depends on the joints that lie between this body and the ground. So if I take myself and I connect myself rigidly to the ground, so I'm not doing a floating base, but now through my legs I'm connected to ground. The motion of my pelvis depends on what my legs are doing, because between the pelvis and the ground, they're my legs. My pelvis is not going to move if my arms do something, right? The motion of my arm depends on the motion of my legs, as well as the motion of my shoulder, and the motion of the hand depends then also on the motion of the elbow, right? Upper arm does not move if the elbow moves, right? Does not move when I move with the right arm. So there's a certain importance here that stuff that connects me to the ground is important. And so I'm basically going backwards along these arrows until I can hit the ground. Mathematically, this is a directed graph, and more specifically, it is a directed tree graph. That comes with 4 conditions. Number 1, it's a directed graph. We have that. Number 2, it is fully connected. If we don't have a physical connection, we would introduce a virtual 6 or 3 degree of freedom joint to basically get a full connection here. I don't want 2 independent graphs, right? I want everything connected. There's no loops in this. And what that means is that from each body, I have one unique path to ground. Not 2, not 0, right? That's basically this condition, no loops, no, everything is connected. And you see that just by going backwards through these arrows, I can always reach ground. That's a property that we will need a lot in the future. You have this in your template to introduce some naming conventions. And I will start with the circles, which we will call the nodes of our tree, and the arrows, which are directed, and those are edges. That's an edge. There's one special node which we call root, and in mechanical system that's always ground. And root is the only node that doesn't have an arrow coming in. Yep. Every other body has some incoming arrow, and that incoming arrow somehow connects it to ground, to the root. Root does not have that. And then we have these guys here, which have no outgoing arrow, and we would call these the leaves of the tree. For us, the nodes represent bodies of our mechanical system, sometimes called bodies, sometimes called segments, links. It's all the same thing. The edges correspond to joints that connect bodies. Root is always ground, where we say ground is something that is rigidly connected to this inertial frame of reference. So ground is not moving. And the leaves in robot language would be called end effectors. No, because there's more, right? Just sort of indicates there is more to this kinematic tree that I haven't drawn there. Yeah.
How would a loop look like? A loop in a tree graph?
There's no loop. It's not allowed.
How would a loop?
You would get basically something like this in a graph. And then you would have more than one path to go back to ground, right? You can go this way or that way. And we're explicitly saying that doesn't exist, right? There's a unique path between every body and ground. That's very important. That's why we don't do loops now. Yeah, well, good point. Thanks.
I was just going to say, like tying your shoelaces together.
Yeah, I don't want to do that. But we'll get to this, right? Couple of weeks, well, more after Christmas, we will talk about loops. But for now, I just want to do this with kinematic trees. If I think in terms of this joint here, I would call ground the predecessor body. And this here would be the successor body. And for joints, it's simple, right? In the graph, there are the edges of the graph. They always connect one node to another. So every joint has a predecessor body. Every joint has exactly one successor body. In Simscape, those were called base and follower. Right? Base is just another word for the predecessor body. Follower is another word for the successor body. And there you see how the direction of the arrow matters. If I think from the perspective of bodies, and I do this now with a green dotted line, this would be the so-called parent joint. So the joint that connects a body towards ground, that would be called the parent joint. Every body has a parent joint with one exception. Ground. Ground itself does not have a parent joint. This here would be called a child joint. And we already see that this body 1 has multiple children. So I say child joints, plural. A body can have one child, right? And if you only have one child, then you would be basically be back to a kinematic chain, where every body has exactly one child joint. Here we have a tree, and whenever you have more than one children, there's basically a branching of the tree. Again, there's an exception. Which bodies don't have child joints? The end effectors, right? So that makes sort of the structure a little bit more complicated from the perspective of bodies, because you may have a parent joint unless you're root. You can have child joints, maybe one, maybe multiple, but you could also not have a child joint, and then you're a leaf. somehow we have to get this into code, right? We have to figure out a way how we can implement the structure. And right now we're just talking about what's connected to what in a computational framework, in an algorithm. And that question is surprisingly connected to the question of what's the best way of waiting for a bus. We have two situations. On the left, London, UK, people waiting for the bus. This is during a subway strike, so people really had to get on the bus, and buses were overcrowded, so it's really important that there is an order in which you arrived at the bus stop and how to get on the bus. On the right, we have the similar scenario in Havana, in Cuba, where people also wait for the bus. There, buses can also be overcrowded, so it's again important when you arrive. Question, of course, who does it better? Or, as you know, right, if you're experienced in psychology, if your instructor asks this question, why is the system on the right better? Because if you just look at the picture, I mean, come on, look at this. An immaculate line with equidistant spacing between the individual participants as well as to the curb. I mean, can you do this any better? I mean, of course, I picked the picture to, fulfill the stereotypes of people in the UK being very good at standing in line. And then you have the total anarchy on the right. Has any one of you been to Cuba? Do you know how this works? Because there's a line here, and it's actually pretty clever. When you get to a bus stop in Cuba, and you arrive there, you ask, ¿Quién es el último? And then someone will raise their hand. Yeah, you just ask who is the last, or who's the last who arrived. And someone will raise their hand, and you just remember who that person was, right? And maybe that person also remembers you, right? And then you wait, and if someone else comes and asks, ¿Quién es el último? Right? You raise your hands and memorize who that person is. If you're a tourist, someone will do this for you because it's super confusing if you don't know how this works. Very embarrassing. But the bus comes, right? The first person who gets on the bus is that person, who arrived first when no one was there, or, didn't get on the previous bus. And everyone else just looks for the person they memorized and then get on the bus immediately after them. So people will get on the bus in exactly the order they arrived at the bus stop, right? It's a completely fair system, but it allows you to do this while you wait for the bus, right? They are sitting back here, they can sit down, they can chat. These people can chat as a group, even though they may arrive at completely different times, right? They're just chatting. She's not even waiting for the bus. She just has to read the newspaper, right? She would love to talk to her friend back here, but they can't, right? Because they're sitting at different points in the line. And if they want to talk, they would lose their spot in the line. So I would argue that this is way, way better. Yeah? How do we call this in computer systems? A linked list. So this is, not 3C, linked lists. So in the UK, you basically store things in an array. Item 1, item 2, item 3, and so on. Each in its neat little space in a memory cell, right? You literally see the memory cells here in this line where everything is stored. And then if you want to rearrange stuff, it gets really nasty. Whereas in Havana, people just hang out wherever they want, or objects hang out in memory wherever they want. Item 1, item 2, item 3, item 4. I can draw them wherever I want. And I then just have to establish these connections where I say item 2 comes after item 1, item 3 after item 2, item 4 after item 3. And I can also establish the connections in the opposite directions, which would give me a double linked list. And you already see that this looks very, very much like the graph we draw before. There's going to be an important difference when it comes to implementation, but we get to this in a second, right? So the idea is basically that I have no central storage, no array, no data object that somehow represents what is connected to what, but we do it in a decentralized way, no central data storage. In a decentralized way through these linked lists. Through linked objects. So for a kinematic tree, we somehow have to represent bodies and joints. And we represent them in objects, in object-oriented programming, right? This is what we already did. We have a coordinate system that is an object. We already had a dynamic body, which was an object. And that will contain information about the body. I'll just say body data. Right. So basically everything that we've implemented so far, mass, inertia, graphical representation, angular momentum, velocities, and so on. That's all body data. And then we have to remember which object was the parent joint. And what are the child joints, right? The parent joints, that was the previous page, the dotted blue line, green line, the child joints, the dotted blue line. And a body should also remember, is it a leaf, right? So some flag is leaf, is root. Joints. We haven't implemented joints yet, but you can imagine there's going to be some joint data. What type of joint, what's the joint angle, what's the joint axis, and so forth. They just need to remember a predecessor body. And they need to remember a successor body. And there's always going to be exactly one predecessor body, exactly one successor body. We had solid green and solid blue for these. So from the perspective of the joints, this one would have ground as predecessor body, this one would have ground as predecessor body. These two would have body 2 as predecessor body. This would the successor body of that joint. B2 is the successor body of this joint. Here the same. And I'm missing an arrow. I can just add that there. And then parent joints. Ground doesn't have a parent joint. This is the parent joint of body 1. This is the parent joint of body 2. Parent joint of body 3, of body 4. And then these are the child joints. Ground has 2 children. Body 1 is a leaf. Body 2, again, has 2 children. And body 3 and body 4 are leaves. Yes? That's basically what you want to make sure that you don't ask somewhere in your code, call something of your parent joint, and parent joint is a null pointer, right? So that's where you have this flag that says, if not root, then do. Yeah. What's the difference between here and here, or between this and sort of the standard linked list that you've seen in your computer science classes so far? That we have
more information here. Because on a double linked list, you can only know two things.
We have two different things, right? So we have bodies and joints, and we always alternate, right? So bodies point to joints, joints point to bodies. And this, of course, goes in both directions. And in the standard linked list, you just have object, 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 and they all connect to an object of the same type. And here we have objects of two different types, which also means that if I look at this, it's not exactly what I have here, right? Because here I have a link, a connection between two objects. Here I have a connection between two bodies, which is a joint. And so basically, you should always think of it in this way, that I have object, body object, joint object. Here are the connections that I see here. Joint object, body object, here are the connections that I have here, right? So that's an important distinction. Small detail, but of course very important, right? And that basically means that the data and the topology are stored in the same object, right? The same object that contains the mass, the inertia, now has a couple of more variables, and they basically point to what are the joints attached to me. And the same object that stores information about the joint, joint axis, joint angle, and so on, also has information to which bodies this joint connects. In a decentralized way. Yes?
About the statement of the decentralized, you said no central data storage. What do you exactly mean?
Well, there's no global variable like this that says, body 1 is connected to joint 2, body 3 is connected to joint 4, right? That doesn't exist. There's no variable in the main program. The connections are only stored.
About the array, right?
Yeah. So we don't have this. All the information is stored in these individual objects. So each body knows to which joint it is connected. Each joint knows to which bodies it is connected. But no one has sort of the overall overview. That's what I mean with decentralized.
Coding language, you mean like you cannot just access anything in the middle of
No.
which is like decentralized, but you have to go through the sequence.
Yeah. I show you a quick MATLAB example where I have created two dummy classes, linked body object, linked joint object. They are really just small classes that have a public property that I just call description. In an actual rigid body, this would be where you have the mass, the inertia, the coordinate system, the transformation matrices, everything. Here I just have a description. And then here I have as private properties, I have parent joint, child joints, number of children, is root, is leaf, right? And here you could say this is a little bit redundant, but sometimes that is quite useful. Yeah.
Say you're going from the root to a specific leaf and
Yeah.
it's branching the way it is in diagrams. Would it have to go through each pathway to find
We'll get there. We'll talk about algorithms in just a minute. But I first want to talk about sort of how to set up this linked list, right? So here's my body object with the parent joint, child joints, and so on. And then I have here my link joint object, which again here has just a description, but in the real implementation is going to be joint axis, joint angle, velocity, and so on. And here much simpler, predecessor body, successor body. So in my main code, this is example 7 that you will get on Thursday with the new set of exercises. Clear all, close all CLC. Creates a clear slate, and then I first create 3 bodies. Ground, how are they called? A, B, C. And I create them without any arguments in the constructor. And if I look into the linked body object, there's my constructor. Doesn't do anything. But remember that isRoot and isLeave have been initialized to true. So each of these now thinks it's root and a leaf at the same time, which makes sense because we haven't done any connections yet, right? The connections come now when I create the joints. So I have a joint 1, and here in the constructor I apply 2 arguments. I say joint 1 connects ground to body A. And then what else do we have? Joint 2. So this was 1. This is 2. And this, I think, was 3, right? A2C or B2C? What did I do? Ground. Oh. Here we go, right? I now established a structure. Let's see what happens in the corresponding constructor of the joint object. And there's actually 2 things happening. Number 1, the object, right? This is this weird MATLAB syntax where you say object's predecessor body, which is this variable, is equal to predecessor body, which is this variable. Right? That's just MATLAB syntax to make sure you store information actually within the object. So you remember your predecessor body, you remember your successor body. And then you tell your successor body, hey, successor body, set parent joint to object. So this joint would tell its successor body that it itself is its predecessor, its parent joint, pardon me, right? And it would then tell its predecessor body, hey, I'm one of your child joints. So this is a child joint, set parent joint, which are basically remembered, right? If I have a set parent joint, I get object parent joint equals parent joint, remember the value, and then of course you set this flag is root to false, because if you have a parent joint, you're not root anymore. With the children, you basically, with the child joint, you increase the number of child joints that you have by 1. You remember that. Here we actually have an array, right, of child joints, because it could be multiple. And then, of course, you set your isLeave to false. If you want to be safe, I could have made here a question, right, a catch an error and say, if I'm already not root and someone says set parent joint, you screwed up, right, because I can only have one parent joint. That could be something that we could try to catch. And then at this point, I have fully established a double linked list, right? Every joint knows predecessor, successor body. Every body knows all their child joints, and every body, if it has one, knows their parent joint. Question. I did it in this way, right? I created the bodies first and the joints second. Could I have done it the other way around? Create the joints first. So, create joints in a first step and then create bodies in a second step. We could have done it, but it's much more complicated, because if I create the joints and I now create a body, I have, maybe I start here. If I do it this way, right, I create the bodies first, and then every time I create a joint, I know it has exactly 2 arguments, predecessor, successor. Here, if I create the joints first and now create the bodies, it may be root, then it doesn't have a parent joint. It may not be root, then it has a parent joint. So I have to basically tell the body when I create it, are you root? If not, what's your parent joint? And then with the child joints, right, it could be 0 if it's a leaf, but it could be arbitrary many. So it's possible to change the order, but it would be much more inconvenient because in my code I would have to account for many, many more different cases. Whereas if I do it in this order, I create the bodies, and then when I create the joints, it's always one predecessor, one successor. Good. We get back to this later. Now to the fun bit. Algorithms, right? So far we just established the structure, stored stuff in memory with this idea here. And now I want to compute x of q. And I want to do this. This is going to be fun. Fun for me. I want to do this with an example, and I call this the CDR laser light robot. It's a very simple robot that consists of a base that is connected to ground, and to make this more interesting, already carries 2 child joints. One of them is a single link. The other, again, is a link that branches off and carries 2 child joints. So this would be link 1. This would be link 2. This would be link 3. And this would be link 4. These 1, 3, and 4 are our leaves. And as end effectors, we have powerful laser pointers, which shoot laser beams into the sky. And the only thing I'm actually interested in is at what angle, right? So alpha, beta, and gamma would be the angles at which we shoot lasers. And those 3, that's why I wrote them in green, are basically my x, right? For the silly robot, x is going to be alpha, beta, and gamma. And we have 4 joints, which I call A, B, C, and D, with, maybe I immediately call them Q1, Q2. You can call them whatever you want. But each of them has an individual joint angle. And you can kind of see how the angles alpha, beta, and gamma follow from Q1, Q2, Q3, and Q4. Looking at this from the outside, it's also quite simple to say that gamma is Q2 plus Q4. But we want to do this now in a recursive algorithm where I want to put together this this robot using U as bodies and joints. So I'll start with root. What's your name? Marcus. Okay. You have 2 joints, right? So this would be ground. Marcus has 2 joints. Who wants to be Marcus' first joint? Joint number 1. I'm not going to pick you. How about you?
Yeah, Tobias.
Tobias. So this is Tobias, joint number 1. And Jan is going to be joint number 2. Here we have body 1, body 2. Who wants to be body 1? What's your name? Noah. Oh yeah, I remember that. We already spoke. Noah. Body 2, maybe the row behind Jan. What's your name? Aves. Can you help me how to spell this? A. Aves. Good. 2 more joints connected to Aves. Joint number 3. What's your name?
Sarah.
Sarah is going to be joint number 3. With an H somewhere? No? No H's? What's your name? Tan. Joint number 4. And then we have 2 more bodies. What's your name? Tian? Tian would be body number 3. And then over there, Lucas. K or C? K. Lucas, body number 4. Okay, so, and then I'm of course the main program, right, as things go in classrooms. So what I would do first is I would create bodies. And I would just say, hey, Marcus, your body. Jan, you're a body. You were a joint. Did I screw this up? Oh, sorry. Noah is a body. Avis is a body. Sarah is a body. And Tan is a body. Tian. Sorry. No, you're joined. Lucas and Tian. We're working on this. Still have a couple of months to remember names. At this point, you all think I'm the king of the world. Your root, your leaf, you know everything. Yeah? And then I create joints. And the way I create joints is that I tell here, Tobias, you're a joint. And you connect Marcus to Noah. And now Tobias does 2 things. Number 1, you remember this. Who do you connect?
Marcus and Noah.
Good. And then number 2, what do you do?
I tell Marcus that he's my, that I'm, what is it called? He's my predecessor.
No, be careful. So he's your predecessor, that's correct. But what do you tell him? And to be honest, the bodies are pretty stupid in this game. You have to tell him exactly what's going on. You are his child joint. Right? So you tell, hey, Marcus, I'm your child joint. Now you remember that, of course. And you also, oh God, I'm not a leaf anymore. Right? You remember you're not a leaf. What else do you have to do?
I have to tell Noah. It's I'm his parent joint.
And now you remember that. He's your parent joint, also not root anymore. Right? Life got a little bit worse. Then I do the same. I say, Jan, you're a joint. You create Marcus with Avas. Remember that. Hey, Marcus, I'm your child. Hey, Avas, I'm your parent joint. And then I do the same with Sarah and Tan. And at that point, the structure is established, but just locally. Right? If I would ask Jan to draw the tree, he would go ahead, oh, there's me. I know that. And then I somehow connect Marcus to Avas. This is as much as you know. Nothing else. Okay? Now, I am, of course, interested in solving this laser light problem. So what will I do? Right? Here, body number 3, Tian. I will ask you, hey, what's your angle? Right? What's your orientation, or what's the angle of your body? What's your answer? You have no idea. Because think about what you know as an object. You know that you're a body. You know that Sarah is your parent joint. And because of that, you know that you're not root. And if you're not root, you have basically no idea what your orientation is. Right? So you could just tell me, I don't know. right? But what could you do in this situation? You can ask someone else for help, right? Who can you ask for help? Yeah, because the only one you know, your parent joint. So you ask your parent joint, hey, what's your orientation? Or what's my orientation? This is where actually bodies, I say, are stupid. You ask, hey, Sarah, what's my orientation? And then Sarah doesn't know because she's smart. She can do math because she's a joint, but she doesn't know what is the orientation of her predecessor body, of Avas. Right? So she would ask Avas, hey, what's your orientation? And Avas is like, I have no idea. Right, and can't even do math, but he would ask Jan, hey, what is my orientation? What's my angle? And Jan doesn't know either and asks Marcus. And now you're the king of the world because you're 0. You're like, I'm root. I know what I am. By definition, I'm at position orientation 0. I'm 0 degrees. You can answer Jan. Right? Now, you have some joint angle. You can make up some joint angle. Actually, all the joints can make up some joint angle, right? And you can now answer Ava's question. He asks you, what's my orientation? So pick an angle, pi over 3. So Ava's orientation is pi over 3. You can now answer Sarah's question. And Sarah can answer Jan's question. You have to do a little bit of math, right? You're joint, so you have to somehow add your own joint angle. I don't know what it is. And then you can answer. Yeah, but you ask her. You're still waiting for your answer. What was the question was, what was my angle? And the answer was? Pi over 3. So you just set your angle to 0. Okay. And then you can answer me. Should we try this again? So all the joints, think of an angle. Maybe we take degrees, some simple degree value, non-zero. And then Lucas is already hiding because he knows what's happened. Hey, Lucas, what's your angle?
I don't know.
No, wrong answer. We'll not take that as an answer.
I have to ask 10.
Then go ahead. And can I just small distinction? You ask what's your angle, but that's not true because a body asks a joint what's my angle. You cannot do math because you don't know what joint angles are. So you would have to ask what's my angle, and then you ask Avas.
What's your angle, Avas? Yeah. I ask Jan, but it's like my angle.
You have to answer him.
My angle is 45 degrees.
Your angle, right? So you're as a joint. You see how the joints are smarter in this game because they do the math, and they basically, oh, this body is this, so that body has to be. I forgot. 45 degrees. What did you say? 45 degrees.
My angle is 45. My angle is 45 plus 25. 70.
My angle is 70 degrees.
Thank you. Right? This would be called an inward pass. So I can probe any body in my system and ask for, in a sense, its x value. And if the body doesn't know, they would just keep asking. And the joints keep asking. And the joints are the ones who do the math, right? They're a little bit smarter in this game. The bodies just store information and pass it on. There's a, yes?
Good question. Can't, like on the first cycle, can't you just, like when you ask the joint, can't you just tell me my joint angle and then add up while going backwards? So starting from the end to the top, which would take, I think, less computational or faster. Because you have to go a full cycle to the ground and then.
But this is, I mean, in code, right? Every time you ask a question, it's a function call. So it doesn't matter in which order you do this, right? So it's basically every object called some function. Get position, get position, get position, get position. These are the calls, and the answer is as soon as that function was executed, right? And you basically get the stack of function calls until you get to root, and root will just answer 0, and then the next function can be evaluated, and so on and so forth. So this would be the inward pass. Sometimes I want to update everything in the tree, where the first thing would be I set joint angles. Again, the joints can think of a value, right? Some random value that I don't even know. And now I can start an outward pass where I would start at root, and I would say, Marcus, can you please update your subtree?
My angle is 0, I tell Tobias and Jan.
So you just store this. Your root, so you remember this first, yeah, you're 0. And then you say, my angle is 0, and you say this to Tobias and Jan. And maybe let's start with Tobias. Tobias. Got this mixed up. So you tell him, my angle is 0. Can you please update your subtree? Tobias is a joint. He's connected to Noah, right? So what will you do? No, you're joint. Right? So you again have to do some math, right? So he just told you his angle was 0, you're joint, so Noah, your angle is pi over 4. Right? And now, and at the same time, you also say, please update your subtree, because I want this to continue. Right? So please update your subtree. And then Noah, you have no children, you're leaf. So you can basically go back and say, I'm done. And then you can tell Marcus, I'm done. And Marcus is not done.
Then I tell Jan, my angle is 0, please update the subtree. Your subtree.
And then I have to tell others his angle.
Mm-hmm.
Let's say 40 degrees this time. And please tell Sarah and Tom.
But you can say that. You have no idea what Sarah, right? This is your view of the world. This is your limited perspective. But you can tell him, please update your subtree.
Your angle is 45. Your angle is 40. 40. You said 40, right?
Yeah,
40, but this is your angle, right? Your body, again, you don't do any math. You just say, my angle is 40 degrees.
40.
Please keep updating, right? And then we would do this one at a time. So we probably go Tan first. Your angle is 40 degrees. Oh, my angle is 40 degrees. Tan.
And update you that
Yeah.
your angle is 50 degrees. Please update.
Then my angle is 50 degrees.
Good now. And you're happy, right? You can just report back, I'm done. You're done. You're not done. Oh, no, you're done, but Avas isn't done. Because you still have a second. Don't forget about your second child. I know that.
Your angle is 40, then update your subtree.
Your angle is 60. Copy that.
And then it goes back, done, I'm done, I'm done. And you tell me. And I know without talking to anyone apart from root, as a main program, everything is updated now. This would be called the outward pass. In general, what we're doing here is using recursion. And it's a bit of a divide and conquer algorithm, where I will start with the outward pass. What I want to do is I want to update the entire tree. And the way we do this is I call sort of this outward pass of my root. And then the root does the divide and conquer step. We divide this now into 2 simple steps, or simpler steps, where number 1 is compute what's happening across that joint, and then update some subtree. So I get basically the same problem again. I went from update the entire tree to update some subtree, plus do some computation across the tree. And I've made the problem simpler. And then I repeat this process where I take my subtree, make it even smaller. In this case, I'm actually left with the leaf, which is the smallest subtree. And when I'm at that point, it became trivial, right? Updating just one body just means storing the information. In a sense, I'm taking this problem, doing a little bit, and recreating the same type of problem, just a little bit smaller. And I keep doing this until the problem becomes trivial. That's what I mean with, in a sense, exploiting self-similarity. Right? And in the outward pass, I basically say that a subtree has the same structure as a tree. So whatever algorithm I use for the tree, I can use for the subtree, and I keep doing this until I get to a leaf. For the inward pass, similar idea. I want to figure out what's going on along a branch. If I ask one leaf, sort of, what's your angle, I want to know what is happening along this branch. And I do sort of the same idea of divide and conquer. I say, I have some joint motion between these two bodies, and then I treat this body here as the leaf of some subbranch. And then I do this again, right? I break the problem into something I can handle, what's happening across one joint, and what's happening in the rest here, right? And this now would be, of course, root, which is the smallest subbranch. And again, we reached a point where the problem became trivial, because if I'm just looking at root, I know the angle is 0. So I can solve it for the smallest sub-branch, and I have some way recursively going from a longer branch to a shorter branch. And I apply or keep applying this until I end up with the shortest possible sub-branch. Thanks, everyone, for participating. Keep this in mind, right? There's bodies talking to joints. I think what's important to remember is how much information each body has. And I know this seems silly to you, but my experience is that once we implement this, it feels like magic. Because no one really knows anything. Every body just asks another body, and you don't really know what's going on if you don't have, in a sense, this overview in mind. With this, I would stop here. Outward pass, inward pass, we will formalize this on Thursday. Also try to do homework 27, so we can talk about this in class as well. Has to do with Jacobians. Thanks.